Lesson 7J, half Atwood machines with no friction. An Atwood machine is a two-body system with a pulley in between the two masses. A half Atwood machine is a pulley device that has one mass suspended while the second is resting on a supportive surface like a table. Recognize that the force applied is due to the hanging mass. We will be looking to calculate acceleration and tension in grade 11. Let's calculate acceleration of our half Atwood of the 2 kg mass labeled M1 resting on a table connected by a string and pulley to the 4 kg mass labeled M2. Here are the forces acting on mass 1, force friction and force tension. Here are the forces acting on mass 2, force tension and force gravity. The coefficient of friction is 0, and we will assume that the pulley is ideal, meaning it's frictionless too. This makes the entire system frictionless since we are ignoring air resistance. As you can see, the applied force acting on this system is force gravity acting on mass number 2, M2. So we can say that F sub A equals F sub G2. A pulley system such as the Atwood or half Atwood machine simply changes the direction of forces, and as a result changes the direction of velocity and acceleration. To calculate net forces, it may be easier to see the forces acting on the masses if we straighten out the system into a single plane, like this. It is important to note that when doing so, we change the direction of the forces, so we must refer to our original drawing or the free body diagram for directions. So looking at the new drawing, we can see that F net is F sub G2 minus tension plus tension minus force friction. The system is frictionless, so friction is 0 and the tensions cancel out, leaving F net equal to the force gravity on mass 2. Remember, F net is mass times acceleration and force gravity is m times g. So now we have ma equals mass 2 times g. The force of gravity acting on mass 2 accelerates the entire system of two masses, so subbing in values we get 2 plus 4 kg times A equals 4 kg times 9.8 newtons per kilogram. That makes 6A equal to 39.2. Isolating for A, we have 39.2 divided by 6. Acceleration is 6.53 newtons per kilogram, or equivalently 6.53 meters per second squared. Referring back to our original diagram, we see that mass 1 accelerates to the right at 6.53 meters per second squared, while mass 2 accelerates downwards at a rate of 6.53 meters per second squared. Calculating tension can be achieved by choosing either mass. We will choose mass 1 to begin with. Tension wins the tug-of-war at mass 1, since it moves to the right. F net equals force tension on mass 1 minus force friction. There is no friction, so F net is force tension at mass 1. The formula for net force is ma, so m1 times A equals force tension at mass 1. That makes tension at mass 1 equal to 2 times 6.53. Force tension at mass 1 is 13.1 newtons. We will now confirm force tension by looking at mass 2. In this case, force gravity beats out force tension at mass 2. The mass falls. Net force equals force gravity minus force tension at mass 2. Isolating for tension, we get tension equals force gravity minus F net. Remember, force gravity is mg, while F net is ma, so tension equals mass 2 times gravity minus mass 2 times acceleration. Subbing our values, we have force tension at mass 2 equals 4 kilograms times 9.8 newtons per kilogram minus 4 kilograms times 6.53 newtons per kilogram, which we calculated earlier. Tension is 39.2 minus 26.1. Force tension at mass 2 is 13.1 newtons, which is the same as force tension at mass 1.